we're going to look at the law of conservation of energy and how that can be used to predict how much energy will be available to change into something else. We'll also talk about efficiency, which is our way of saying, does all that energy really end up being available, or do we lose some along the way? Okay, so the law of conservation of energy tells us that energy in the universe cannot be created. It cannot be destroyed. Okay, what's there has always been there, and it will always be there. We can't get rid of it, and we can't make new energy out of nowhere. Now, it might seem like we can make new energy out of nowhere when we have big power plants that generate electricity from seemingly nothing, but it always comes from something. There has to be a source of it. We're just really clever at changing types of energy from one to the other to make it useful and usable for us. Okay, so even when we lose track of energy, energy is conserved. Okay, in other words, it's all got to be there. Okay, so let's go through some examples. Let's see with this first one. So I have a bouncy ball. I'm holding about 30 feet up from the ground. I think I'm the Schoology version of this. I say 3 feet. But either way, I'm holding the ball up. So it has potential energy. Okay, in other words, it has the potential to fall. Gravity is pulling it down. Okay, and therefore it has the energy to potentially move. Okay, the amount of energy is measured in joules. So right now, holding up the ball, it has 4.0 joules of energy. Okay, now when I drop the ball, it moves faster and faster, so that potential energy is converting into kinetic energy, the energy of motion. Okay, so when the ball's moving the fastest right before it hits the ground, we should have no more potential energy left because it's almost just about on the ground. And instead, all that energy should have been converted into kinetic energy. Okay, so according to the law of conservation of energy, all of that energy should still be there. If I started with 4 joules of energy, I should still have 4 joules of energy wherever the ball is in this path. Okay, so as long as I haven't lost any along the way, and it doesn't say that we've lost any so far, all that energy should still be here. So if I started with 4 joules of energy, I should still have 4.0 joules of energy now. But now it's in the form of kinetic energy instead of potential energy. Okay, energy is energy. Okay, measured in joules. So I still have 4 joules of energy. It's just a different type of energy now. It's now the energy of motion. It's kinetic energy. Okay. Now, realistically, we do end up losing energy here and there as things bump into each other and there's friction or electrical resistance. Energy tends to get lost along the way. It's actually really hard to keep track of energy and making sure it doesn't get lost. Okay, so let's look at some examples of how we deal with that. Okay, so when the ball falls and hits the ground, it stops for just a moment. So all that motion stops, which means we no longer have kinetic energy. Instead, it's converted into potential energy from the ball squishing and compressing and trying to unsquish itself, and thermal energy, which would be like heat from the friction of hitting the ground and rubbing against it. Okay, so 70% of our ball's energy is going to be potential energy. And we want to figure out how much or what percentage of the ball's energy is changed to thermal energy then. Okay, so 100% of our kinetic energy is changing, okay? Just like how we started with 100% potential, which changed to 100% kinetic. Now that 100% kinetic is changing into 2 things. 70% of it is potential energy, and the rest of it is thermal energy, okay? But all that 100% energy still has to be there. That 4 joules of energy that we started with here, 4.0 joules, and here, 4.0 joules, still has to be here. We still have to have 4.0 joules at the end here, okay? So if only 70% of it is potential energy, the rest of this, to make 100%, will be the thermal energy. So what's 100 minus 70%? You can do this in a calculator, or you can do it the old-fashioned way by hand. So 100% minus 70% should be, so put it in one, take it one, that should be 30%. I would recommend using a calculator, and some of you might be able to do it in your head with mental math, which is cool. Okay, but we should have 30% thermal energy here, just from the friction and stuff. And this is the reason why the ball doesn't bounce as high the second time, and why it bounces even less high the third time. It bounces short of the fourth, the fifth, and the sixth until it finally stops. Okay, we're losing that energy as thermal energy, as heat from friction, each time it hits the ground. Okay, so let's try another one. All right, so in that moment when the ball hits the ground, we said that 70% of its energy becomes potential energy and 30% of its energy becomes kinetic energy. Okay, now in this case, we have the actual measurement of joules. Okay, so 70% of this 4 joules that we started with is 2.8 joules of potential energy. Okay, so that's our potential energy right there. We got 2.8 joules of it. What we want to know is how many joules of thermal energy we should have released from this, okay, from that heat, from the friction. Okay, so not just the percentage, we want to put a number on it. What's the measurement? So if I can't have any more than the original 4 joules of energy that we started with, 4.0 joules, and 2.8 joules of that energy was potential, the rest of it has to be thermal. Okay, so again, this is just a little subtraction, and I would recommend doing this with a calculator or with some really good mental math, but you could do it the hard way like I am. So I'm going to take 1. I don't even know if they teach math this way anymore. So you carry a 1, so that's like 10. 10 minus 8 is 2. Drop our decimal point. This has gotten knocked down because we carried the 1, so 3 minus 2 is 1. So this is 1.2 joules of thermal energy now. Okay, so that 30% of 4.0 joules is going to be 1.2 joules. Okay, let's look at some more examples. Okay, in number 5, we're looking at a coal plant where you burn coal, and that chemical energy from the coal is turned into thermal energy, then kinetic energy, and then electrical energy. Okay, so we end up going through a process in a power plant to turn a turbine with steam, with boiling water, and that energy moves some magnets around some copper wire, or copper wire around some magnets, and you can use that to pull electric charges or electrons through a wire to make electricity. Okay, so long story short, we start with chemical energy from the coal, and by burning it and going through that whole process, we end up changing all that energy into electrical energy. Okay, so from 1 gram of coal, we can get 29,307.6 joules of chemical energy. Okay, now if this was a perfectly efficient process, which means no energy is lost from friction, electrical resistance, anything else, how much electrical energy can be generated from this 1 gram of coal burning? All right, well, if we lose no energy, okay, in other words, all the energy that we start with is what we end with, then all that energy should be there, just in a different form. Kind of like our ball changing its potential energy into kinetic energy. It started with 4 joules of potential, and all that potential energy is changed into kinetic energy. So we start with 4 joules, we end with 4 joules. So in this case, when we say perfectly efficient, we mean basically the same thing. No energy is lost, so whatever we start with should be what we end with, even if it's a different type of energy. So 1 gram of coal that could be perfectly efficiently burned to generate electricity should be able to make a maximum of 29,307.6 joules. Okay, so there's no math here. It's just knowing that all that energy is conserved. It's all still there somewhere. Okay, now this isn't a very realistic way of imagining things, but this would be the perfectly ideal way. And there's no way we can get more than this energy out of this process. Okay, unless you're cheating something, you're sneaking in energy in some other way. Okay, so this 1 gram of coal can push out this much and no more than that. Okay, now it is possible that we end up with less energy than this, not because the energy is destroyed, but because it gets lost along the way. So in a coal plant, for real, it's not actually perfectly efficient. We end up with less than this maximum number of 29,307.6 joules. Okay, only about 40% of that amount of energy ends up becoming electricity, and the rest is lost along the way as heat, as thermal energy. Okay, now that could come from gears turning and grinding against each other. It could come from the turbine moving, or resistance inside the wires. But in any case, your energy is lost somewhere. So that means in the end, we're not getting all of it to be changed into electricity. So if we have 29,307.6 joules with 40% efficiency being changed into electricity, we're definitely not going to have the full 29,307.6 joules. We're going to have like less than half of that. Okay, 40% is less than half of this. Okay, so to figure out exactly how many joules there are, we just need to multiply this percentage to this number of joules. Okay, that'll tell us which chunk of this is left to become electrical energy. So let's take 29,307.6 joules times 40%. Okay, now your calculator might have a percent button, okay, like this, okay, in which case you need to use it. If you just say times 40 and you don't include this percentage, okay, then it's going to multiply this energy by 40, and then you're going to get a huge number that is way more energy than what we started with. And that breaks the law of conservation of energy. You can't just have more energy for no good reason. Okay, so that's a good sign that something went wrong in the math. So let me take this off and put the percent back. Okay, so the percent sign in your calculator basically treats this percent like the actual number that it is. See, a percentage kind of hides the value of this number because the number doesn't look as pretty when we show what it really is. Okay, so another way to write this, or ... Another way to write this would be 29,307.6 joules times 0.4. Okay. We take decimals like this, or fractions like this, and multiply them by 100 to make them into percents, to make them look nicer. Okay, so to change them back into what they really are, which is a decimal, you can move the decimal point of the percent, which would be at the end, 2 spots to the left, and you get the decimal version of this. Okay, so if your calculator does not have a percent button, this is the actual value of the percent that we need to multiply. Okay, and this should get us an answer that's smaller than the total number of joules that we have to spend here. Okay, so if we were to punch this into a calculator, either by using a percent button or by using the decimal version, which is 0.4, it's 29,307.6 times. I'm going to do times 0.4, but you can do times 40%. We get 11,723.04 joules. Okay, and the rest of the energy here that doesn't show up in this answer gets lost as heat. It would be the other 60% that winds up as thermal energy instead of as electrical energy or electricity. Okay, so this is our answer. Okay, so whenever you're dealing with something that's not perfectly efficient, you just multiply the percentage. In other words, you multiply the decimal version of the percentage. Okay, let's look at a couple other examples. Okay, in this case, we're doing something very similar. We're looking at nuclear energy this time instead of chemical energy, but it's basically the same idea. Okay, so in this case, we're dealing with something that is, again, perfectly efficient, just like number 5. So whatever we start with should be what we end with in terms of energy. Okay, so if we're not losing any of this energy, all of this nuclear energy should be able to change into electrical energy. Okay, as long as we keep track of all of it. So 1 gram of uranium contains about, that's a huge number of joules of energy. Okay, so let's see, that would be 1,000, a million, a billion. So this is 80,600,000,000,000 joules of nuclear energy. Okay, that's a lot of energy. So if all of that was conserved and we changed all of that into electric energy, we would have 80 trillion 600 billion joules of energy. I got to write out all my extra zeros. Okay, I think I got the right number of zeros. All right, and big J for joules. Okay, so it's all still there. It's all still accounted for. Okay, now again, this is not realistic, but some power plants can be very efficient. Okay, if you use some very high-tech engineering and you are very scientific about the whole process and things like that. So in this case, in this nuclear plant is pretty good. It's 93% efficient. So only 70% of that nuclear energy that we're starting with is going to get lost and converted into thermal energy instead of electrical energy. Okay, so in this case, we want to figure out how much of this original 80 trillion 600 billion joules of energy can be converted into electric energy when it's only 93% efficient. Okay, so we're going to take this huge number, 80 trillion 600 billion 0.0000000 joules and multiply it by 93%. Okay, and remember, you can use this percent sign in your calculator, or if you don't have that, 93% is just like saying 0.93. 0.93. Okay, so either way you do it, just make sure you pick one of them and do that in your calculator. So, okay. Now, if you have a phone calculator and you're doing this on your phone, you might need to turn it sideways just so you can fit this number in here. Sometimes your calculator screen's not going to be big enough to fit all the zeros. And it's going to be like, this number's too big, and I'm not going to let you multiply this. So, let's see. Here's 80. 600 and then 0.0000000 times either 93% or 0.93. Okay, so that ends up being still a pretty big number. So this comes out to be about 74958. Let's see. Something like that. Okay. Now your calculator might read this out as something with scientific notation. So if you see something like 7.4958 times 10 to the 13 or 7.4958 e positive 13 or 7.4958 this capital E 13. Those are all different ways of writing the same thing. Basically that this is a really big number. This is called scientific notation. And this means that your decimal point is actually 13 spots to the right. Okay, so if you were to go and move this 13 spots to the right, you end up getting this. This is the number that we're talking about. This just kind of shrinks it down so it can fit on a calculator easier, or on your page easier for that matter. Okay, so there we go. That's in joules. Okay, so not as much as what we started with, because some of it was lost as heat, but still quite a bit. Okay, last set of problems. Okay, now once this electricity reaches a home, it can be converted into all kinds of stuff. So this is kind of the budget of energy for a day for a house. Okay, so let's say this house is going to use 1,000,000 joules of energy today. Okay, it's going to split it between these four types of energy: light, heat, sound, and kinetic energy. Well, let's see. In some cases, we have the percentage of the energy. In some cases, we have the joules of energy. In some cases, we have neither. So let's try and figure out how we can figure out these kind of missing pieces here. So to figure out the number of joules, we've already kind of done this. We just take our total number of joules we have to use and multiply it by a percentage. So this time, instead of it being efficiency, we're just saying how much of this is going towards light, okay, or how much of this is going towards heat or sound or kinetic energy, okay, where we don't think of the rest of it as waste, it's just going to be some other kind of energy. The math is still the same. So I'm going to take that total amount of energy that we have to spend, which is 1,000,000 joules, there's my million there, joules, times, and again, you could say 41%, or you could say 0.41, if you move that decimal point to the left twice, and you should get, let's see here, about 410,000 joules. All right, so that's our answer there. All right. Now, what about this case, the heat? Okay, well, this case we have joules, but we don't have a percentage. So what do we do in this case? Okay, well, we kind of have to do the opposite. Instead of using the percentage to find the amount of joules of this type of energy, we're going to use the joules of this type of energy to figure out the percent. So if we were multiplying before, now we have to do the opposite of that, which is dividing. Okay, so if we take this 330,000 joules and divide it by the total number of joules that's coming out of, which is that 1 million joules, 1,000,000 joules, okay, that should come out to be our kind of fraction or our decimal of this amount of energy out of the total. So I'm going to take 330,000 divided by a million, and I get 0.33. Now you have to be careful because, again, this is the true form of the percentage. This is what the number actually means. But this doesn't look pretty, okay? And this is what the percentage actually is. It's not 0.33%. It's 0.33, the decimal. If we want it to be a percent, we do the opposite of what we did before, and we move the decimal place 2 spots to the right instead of 2 spots to the left. So this ends up being 33%. Okay. All right. Now the sound energy one is going to be just like we did up here. Okay, so I'm going to leave that one for you to figure out. And I'm going to give you a hint on what to do for these last ones on kinetic energy. Okay, so we have all of these types of energy coming from this total amount of energy here. Okay, and all of it has to be accounted for. This is where all the energy is going. It's either going to be light, heat, sound, or kinetic. It's got to be one of those 4. Okay, and all of those 4 have to total up to this amount. So if you figure out the number of joules of light and heat and sound, and it's not quite a million joules, then the bit that's missing has to be the kinetic that we haven't figured out yet, okay? Because energy is conserved. It all has to be there. So if you come up short of a million joules with these 3 types of energy, the amount short you are is how much kinetic energy there was. So it's okay if we don't have a percentage to do some math with or an amount to figure out the percentage. We can base it off of the total and whatever is missing from that total to finish it out to get it to that. Okay, same thing with this percentage. Okay, all my different types of energy here should add up to 100%. Right now we've got 41% and 33% and 9%. If I add that up, 41 plus 33 plus 9, well, that only gets us 83%. So the rest of that percentage must be coming from kinetic energy. So if I take 100% and subtract 83%, what's left is 17%. Okay, so to figure out the kinetic energy, you could either figure out the sound and then just figure out kind of the missing piece that adds it up to a million, or you can do the trick like we did before with the percentages, where you can take this 17% times the total to figure out what the part of energy is here. Just this single type of energy is 17% of this total here. Okay, so that is energy and efficiency and percentages.